So, first off, specific latent heat is the amount of heat energy required to change the state or phase of 1 kilogram of an object or substance at constant temperature. It is important to note that whenever something changes state or phase, going from solid to liquid or liquid to gas, it always happens at a constant temperature. So, for example, when ice turns into water, when it melts, it happens at 0 degrees Celsius. The temperature of the ice isn't increasing, the temperature of the water isn't increasing when that is occurring. So our formula for specific latent heat is E sub H is equal to mL sub V, or E sub H is equal to mL sub F, where we know EH is the heat energy measured in joules, M is the mass measured in kilograms, and LF is the specific latent heat of fusion measured in joules per kilogram, and L sub V is the specific latent heat of vaporization, also measured in joules per kilogram. Why is it that we have an LF and an LV? Well, it's just to distinguish between fusion and vaporization. Basically, it's just one formula, E equals mL. But what is the difference between fusion and vaporization, you may be asking? Well, it's this. When something goes from solid to liquid, that's called fusion or melting. When it goes from liquid to solid, that's called freezing. Some people also call it solidification. When you go from liquid to gas, that is vaporization, and from gas to liquid, that is condensation. If you go directly from solid to gas, that's called sublimation, and directly from gas to solid, that's deposition. So let's look at an example. How much heat energy does it take to melt 25 grams of ice? Given that the specific latent heat of fusion of ice is 334,000 joules per kilogram. So we start by identifying our givens, and in this case, we need to convert from grams to kilograms. Our value stated for the specific latent heat of fusion, we put that down, and then we write our formula. So we substitute 0.025 kilograms multiplied by 334,000 joules per kilogram, and that would give you 8,350 joules. So if you understood, practice on this problem, pause the video here, and when you're ready to continue, you unpause and the video will continue in 3, 2, 1. This is the solution. A 50-gram block of solid metal at negative 20 degrees Celsius is heated up until it melts and turns into liquid metal at 25 degrees Celsius. What is the specific latent heat of fusion of the metal if it takes 7,375 joules of thermal energy to undergo this transformation? Assume the metal changes phase at 0 degrees Celsius and use the specific capacities stated when they're both in solid and liquid form. So let's analyze this problem before we get to working. We have a piece of metal that is in its solid phase, and its temperature rises. It then changes phase from solid to liquid, and then while it is in liquid state, its temperature rises again. Please keep in mind that while it is changing phase from solid to liquid, its temperature does not rise. So this transformation has 3 parts to it. There is the rise in temperature when it is in metal, there is the change of phase from solid to liquid, and then there is another rise in temperature when it is now liquid metal. So, identifying our givens, the mass is 50 grams, which is converted to 0.050 kilograms. The first change in temperature when it is in the solid phase is from negative 20 up to 0, so that is 20 degrees Celsius. The second change in phase is from 0 up to 25 degrees Celsius, so that is 25 degrees Celsius. The heat energy used is 7,375 joules, and the specific heat capacities, we state those as well. Our formula now is simply not one formula but a combination of 3 formulae. MC delta theta for when it is in solid phase and the temperature is increasing, ML when it is changing phase from solid to liquid, and another MC delta theta when it is in liquid phase and the temperature is increasing also. So we substitute our values. We'll have the total heat energy, which is 7,375, is equal to 0.05 times 500 times 20 plus 0.05 times L plus 0.05 times 750 times 25. Simplifying, we'll have 7,375 is equal to 500 plus 0.05 times L plus 625. So 500 plus 625 is 1,125. We transpose that and subtract it from 7,375, and that will give us 6,250. So to find L, we'll take 6,250 and divide it by 0.05, and that gives us the specific latent heat of fusion for this particular metal to be 125,000 joules per kilogram. So If you understood that, which I hope you did, please practice on this problem here. Don't be intimidated by this big number here. It's just another big number. You can easily calculate it, right? Plug it into your calculator. Practice on this problem and pause the video. When you're ready to continue, the solution will be shown in 3, 2, 1. So this is what a basic heating curve looks like. Here you have heat being added, and as heat is being added, the substance starts from solid and then it plateaus where the temperature is no longer increasing. Then it changes to liquid and it plateaus again where the temperature no longer increases, and then it goes into a gaseous state. Here I have this video for you to watch that goes more in detail.
Two key things to note. Firstly, that specific latent heat is particular to state changes. So the specific latent heat to change ice to water is different to the specific latent heat to change water to water vapor. And secondly, that there is no change in temperature during this change of state. It remains constant. The temperature will only change once the state change has completed. As I said before, the heat energy is not used to heat up the substance, hence no change in temperature, but instead used to make or break the bonds that hold the molecules together. If we heat up a plastic fork to its melting point, C between points B and C on this graph, the heat energy it absorbs at its melting point is busy breaking the bonds between the individual plastic molecules. Once enough bonds between molecules have been broken, the fork will melt and become liquid plastic. Messy. After this point, if we keep heating up the melted plastic, a temperature rise will be detected. The temperature will keep rising up until the next state change, liquid to gas. At the vaporization point, the plastic would stop increasing in temperature whilst it transitioned to gaseous plastic. Once in the gas state, if we were to continue heating further, the gaseous plastic would, you've guessed it, rise in temperature. So breaking bonds is why the temperature does not rise or fall when a substance undergoes a state change. Remember I said earlier that it may take a different amount of heat energy to change a solid into a liquid than to change a liquid into a gas? For example, it takes 7 times more energy to turn liquid water into gaseous water than it does to melt ice into liquid water. This means a substance can have 2 specific latent heats. Now let's...
Okay, so if you understood that, then answer these problems here. Pause the video, write down these problem questions, and then unpause it to see the graph that is being revealed now. In 3, 2, 1. Answer the questions based on the graph, and once you have finished, then unpause the video. Your answers will be revealed in 3, 2, 1.